How are you hearing the music you're hearing? To understand that, we need to understand the physics of harmonic motion. An object is in simple harmonic motion when it is oscillating back and forth in a predictable pattern. There are certain terms that we use when referring to harmonic motion. Amplitude is the distance between the highest point of the wave, also known as the crest, and the middle of the wave. This distance should be equal to the distance between the lowest point of the wave, the trough, and the middle of the wave. A graph of harmonic motion shows us that when an object is at its maximum amplitude, its velocity is zero. Its acceleration is at its furthest value from zero, be it positive or negative, and force is opposite acceleration. However, when an object is in the middle of the wave, considered the zero position, its velocity is at its maximum, and both force and acceleration are zero. Most graphs of harmonic motion are sinusoidal. That's just a fun word to say. There are a few other important terms to consider when discussing harmonic motion. Period is the amount of time that it takes for one full oscillation. Frequency, the inverse of period, is the amount of full oscillations which occur every second. The two can even be expressed in the same equation. I've mentioned waves a few times before, but what is a wave? A wave moves energy without any net motion of matter. A wave is created by an object vibrating. A wave we humans are quite familiar with is sound. Sound is a type of wave called a mechanical wave, which requires a medium through which to carry its energy. There are two ways that waves can move. Therefore, we classify them into two different types, transverse and longitudinal. In a transverse wave, the particles in the wave move perpendicularly to the energy. In longitudinal waves, though, the particles move parallel to the energy. Sound, along with being a mechanical wave, is also a longitudinal wave. Along with the aforementioned harmonic motion terms, when specifically discussing waves, a few new terms join the party. A wave's wavelength is the distance of one full period. Wavelength is inversely related to the frequency of the wave and directly related to the wave's velocity, how fast the wave is moving. An equation that relates these two as well as frequency is lambda equals v over f, lambda being wavelength, v being velocity, and f being frequency. A few of the instruments you hear in the music you're listening to right now are stringed instruments: violins, violas, cellos, and double basses. These instruments have 4 strings each, and a bow is drawn across the strings in order to create the sound. Waves have unique properties on the strings. The first important thing to note about waves on strings is that strings experience a force known as tension. This force is an important part of how the strings vibrate. Bowed-stringed instruments, such as the violin and others previously mentioned, use tuning pegs in order to change the string's pitches. The way that these work is that they pull the string tighter, increasing the tension. Since tension plays a role in how the strings vibrate, increasing tension increases the frequency of the sound. It also increases the velocity of the wave. An equation which relates wave velocity is v equals the square root of ft over m over l. M over L is the abbreviation for linear density, another important property of strings which affects how they vibrate. We've talked a lot about the properties of waves, but we haven't taken an in-depth look at sound itself, the key to music. The first important thing to take into account with the physics of sound is that sound moves at a particular speed depending on its medium. Since sound is a mechanical wave, it requires a specific medium through which to carry its energy. A lot of the terms we apply to general harmonic motion can also be applied to sound, but in music we give them different names. In music, we call a sound wave's frequency its pitch, and we call its amplitude its volume. A new term that comes with focusing specifically on sound is intensity, which is essentially another term for volume, except there's a bit more to it. When we talk about intensity, there are a few important things to note. The first is that the sound is emitted in spherical wave fronts, which means that to find the distance from a sound, which is part of what determines the sound's intensity, we need to use the formula for the area of a sphere, 4 pi r squared. The entire equation for calculating a sound's intensity is the power being supplied over the area of the spherical wavefront. I equals p over 4 pi r squared. A common way we describe the volume of a sound is with decibels. Decibels increase logarithmically, which means that a 10 decibel increase actually makes the sound 10 times as intense or twice as loud to our ears. In orchestration, instruments are preferred over others in certain contexts due to their timbre. There is a scientific basis to timbre that relates to all this. Timbre is actually determined by the relative amounts of the same frequency an instrument plays at the same time. Instruments of different timbres have difficulty remaining in tune with each other. I'm looking at you, oboes. And when instruments are out of tune, it's audible. But there's something other than painful dissonance that can be heard between two poorly tuned instruments. We also hear beats. No, I don't mean a drummer is laying down a sick jam to boogie to, but we do hear the constructive and destructive interference between the two waves from the instruments, which causes this consistent wah-wah-wah sound. The beat frequency can be calculated by taking the difference between the two frequencies. There's one more important thing that we haven't covered regarding music as it relates to the physics of waves and sound. That is the harmonic series, commonly referred to as the overtone series in music. The harmonic series is a group of notes that we actually hear above the pitch we intend on playing. For example, if you step over to a piano and plunk down an A, specifically the one above middle C, then you hear an A, specifically A440. The string inside the piano is vibrating at 440 Hz. This pitch of A is what we refer to as the fundamental frequency, but we hear a certain number of overtones or harmonics above that. The first overtone is an octave above the fundamental. The ratio of frequencies between the fundamental and its first overtone is 2 to 1. The frequency is doubled. The second overtone is a perfect fifth above the first overtone. The ratio of frequencies is 3 to 2. The second overtone has triple the frequency of the fundamental. There is also an equation to find the frequency of a harmonic. F sub n equals nv over 2l. There's a lot of complicated terminology and science behind overtones that goes beyond what this video is meant to cover, but this at least gets the idea across. All of this science and more combines to form what we humans know as music. There is plenty more to it than what this video describes, but the goal of this video was a general overview. Physics is really interesting and can be applied to a lot of different things. Sound is just one of those, and it was definitely worth exploring in detail.